10. I'm back, and I do have a kind of a very interesting, probably you will like this one. You don't like the snow fine, which I understand. Nobody likes that. But I bet you that you will like the discussion coming. Very interesting discussion. And it's my agenda for the next 40 minutes is to go and refresh. You will see some information is going to be brand new for you, and some other information it will look just for you like an old, which I'm gonna bring it and revive it because I need it. I said early in the class, this class is very much connected to some stuff that you learned last year in statics, strength of material, and concrete technology, and you will see today lots of information that's from last year. Okay. Probably I'm going to talk about reinforcing bars, mechanical properties, concrete mechanical properties, concrete durability, which is I think the same class had it with me last year. And I'm not sure if we have time. I know there's 40 minutes, and I don't want to really push so hard because of your emotional status. And then I'm going to probably break at this point, and let's see. But we have lots of things to cover in this presentation, which is available, and probably this will cover me until the end of this week. Okay. Let's start. So guys, you know that this is a reinforced concrete design course. Okay. And I guess because of the design course, we need to understand the mechanical properties of those material that we will deal in this class. In other classes, maybe steel, you're learning about steel design. So 100%, you need to know what is the yield strength of the steel, the modulus of elasticity. Same thing here, okay? So I know you got the idea, and probably several instructors, they talk about this one in other classes. Why this thing called reinforced concrete? So why concrete plus rebar? I guess that's very obvious by now for you. Concrete is amazing material in compression. Okay, if you put the concrete in compression, it really survives high load. However, once you change compression into tension, concrete became so weak and doesn't perform well. And if we are able to make our members out of pure concrete, like only plain concrete without any reinforcement, simply it doesn't work very well. It works only if my member has a compression, but as soon as my member has some tensile stresses, then it performs bad. So that's why the idea came, and it never came from an engineer. It came from a mason, and he was trying to make some pottery, and he used cement. And then what he did is he used some bars, placed them in the concrete, and he just kind of noticed that the concrete performs very well, doesn't crack. It's amazing. So from that point, and I think this was back in mid 19th century, and so simply they start putting some reinforcement in the concrete because they know it performs better. But really, who turns this into an engineering was the German. So the German transformed all this into theory and math and design was due to the German. Anyway, there is a long history for that. I'm not really going into the history. There is no time for that. But if you're interested, there are lots of literature on the internet to tell you what's the history of, not concrete, of the reinforced concrete. So concrete, and then we place rebar into it. Okay? So what I'm going to do today is, because we're using two materials, obviously, we're using concrete and rebar 100%. Before we start our design, which is supposed to start very soon, I need to prepare you to understand some concept about and all the mechanical properties of every material of concrete and reinforcing bars. Very important, because trust me, if we go into the design and we talk about yield, and some of you say, okay, what is yield? Then we are in trouble. So I guess it's better to probably spend a few minutes on every slide, better than to go through the pain for you guys not remembering the meaning of those mechanical properties. And you will see it's not very difficult. But let me explain for you And I kind of put the table, the title for this slide. I said concrete and rebar are best friends. Concrete and rebar are best friends. Okay, and I'm gonna show you. A minute ago we said concrete was very weak in tension, very weak. So what did we do? We blazed rebar. So rebar will be blazed primarily in the tension side to take care of the tensile stresses. So this is a favor that rebar does for the concrete. How about the other way? So the other way is concrete provides fire protection for the rebar. Remember, guys, if you have a fire event in a steel structure, steel will just melt. Steel will melt. Concrete is very, very good when it comes to fire protection. And that's why in a concrete, reinforced concrete element, the concrete will protect the rebar from fire. Now, why concrete and rebar are best friends? Because something very, very interesting, the thermal expansion of the concrete and the steel, they are very, very close, very, very close, almost the same. And that's really, it makes the rebar is a good option. And using other material rather than the rebar, even they are strong, it doesn't do well. Because think about it, think about it. If you have a fire event, so we have a heat, and this heat is heating two materials, and they have different expansion. You guys need to feel what's going to happen. If two materials glue to each other, and we apply heat, and everyone has different thermal expansion, so they expand differently, you know what's going to happen. That's why concrete and rebar, they are a very good match. Also, concrete provides corrosion protection. Corrosion protection. We know that rebar corroded due to chemical and electrical process. So it corrodes, and when it corrodes, that's very dangerous. And I'm gonna kind of highlight on the danger of corrosion shortly. Okay, but corrosion is very dangerous, and concrete provides a corrosion protection for the rebar. One of the main secrets that nobody pays attention to of the reinforced concrete is the bond. The bond between rebar and concrete is really the secret. And I wrote it here explicitly. I said the bond between concrete and rebar is the real secret of reinforced concrete. If they don't bond to each other, it means they don't perform together, they perform independently, and your beam is going to fail. Okay, now we know that every time I have rebar and I pour concrete, it sticks to the surface of my rebar, very good bond, and my beam will perform very well. So what is the reason that this bond can be affected? And this will go into probably a practical aspect. Sometimes it rains, sometimes, you know, we place our rebar in mud, and mud plus rain, so you get like those kind of molds that you stick to the rebar, so the rebar becomes dirty and dusty. Now let me ask you, is that any danger when the rebar becomes dusty and then moldy? So if you're doing inspection and you look at the rebar and the rebar is not clean, what can you tell? And what's any input? Anybody who's still awake?
It won't bond as well.
Thank you, sir. It's not going to bond as well. So that's why if at some point of your life and you're doing an inspection and look at the rebar and you look at the rebar is not clean, it means there are lots of debris and lots of dirt on the rebar, then ask for cleaning the rebar. Okay? Ask for cleaning the rebar because you know that the bond will not be the best, and bond is the secret. The other thing which is way more dangerous, which happens after the fact, is simply corrosion. Corrosion is an enemy. As soon as your rebar corrodes, then you guys know that, and I know some of you guys did last year like a research topic on corrosion. Is that in this class? You did in my Civil 222 like a research topic on corrosion, rebar corrosion. I remember there's somebody that this kind of research, which was very interesting. But the thing is, guys, rebar corrosion, what it does, it's a chemical reaction, and it simply splits the last layer, the surface layer of your rebar will disintegrate from your rebar itself, and simply you're completely losing the bond between the rebar and the concrete because the surface layer is simply disintegrated or already not part of the rebar itself. Okay, so as I said before, if you have a corrosion, it's simply bad effect on concrete, bad effect. Not only causes cracking, which it does for sure, because the corrosion has extra volume, which will simply push the the outside layer to the outside and cracks your concrete, but also it has a problem with the bond. It affects the bond, and for sure you lose the cross-section area of your rebar. Let me show you. Let me show you in a picture. The picture will even say it better. So this is a picture of a beam, and probably I can zoom in. So this is a picture of the beam, and you can see the beam, the rebar is corroded, and for sure due to water ingress, huh? And you can see here the outside layer is lost. Like, you know, this is lost naturally, because simply when rebar corrodes, simply it expands and push the outside layer of concrete. And you can see the cross section. Not sure how clear you can see, but the cross section is lost. If I start with a 20 m and after a few years with corrosion, maybe right now I'm 10 m, only 10 m. And I myself have been to some projects where there is no rebar at all. The rebar is completely gone, completely gone. Okay. So concrete, it does protection. And in our course, how do we maintain this protection? By ensuring there is a minimum cover depending on the exposure of our concrete. Okay. Now, I want to talk briefly on this slide. This slide, again, is not new. Anything you see on this slide is kind of old. If you have a rebar and you put the rebar in tension, what's going to happen? And we're increasing the tension from 0, and we keep pulling our rebar until it snaps. Simply, it follows this diagram. Not new. It goes from 0, and this diagram is between stress on the y-axis and between strain on the x-axis. Stress and strain. So what you see here is a stress-strain diagram for rebar under tension. So you apply tension, and what happens is the stress in the rebar will increase and the strain in the rebar will increase until you get to the point, which is very important point, called yield point. So the yield point, look at the name, just like you guys, you are right now probably at the yield point. Okay. When you get yield, you get fatigue, like not fatigue, sorry, those are the different things. But when you get yield, you get elongation. So the rebar, the elongation or the strain will increase without adding any effort, without adding any extra force or stress. Okay. So this is a very significant point in the rebar called yield. And you can see on my diagram, I mark this F yield by F sub Y and this value, and you can see it's roughly around very close to 400 MPa. Okay. Now it's time to talk about the grades, because this is connected to the grade. Not every bar you test will give you 400 at the yield. Sometimes you will get 300, sometimes you get 400, sometimes you get 500 MPa. And that's what simply dictates or dictated by the grade of the rebar. And guys, you know that the rebar is alloy, yeah? It's not steel, it's not iron. The rebar is an alloy, so we add carbon to the iron, and we get an alloy. And it depends on how much carbon we add, we get different grade of steel. Okay. And I guess this information is not new. Probably you will hear it one more time with Corwin in the steel class. But for our rebar, we have 3 different grades, and you can see their names are here. Okay, I'm gonna box this out for you. You can see here is the grades that we have. We have a grade called 300 and 400 and 500. What are those numbers? Those are the yield. When we apply tension, the yield at this level of stress. Okay. Also, we have 2 types of the rebar. We have some called regular, which we refer them as R, and then we have something called weldable, which is W. Now, in our course, and I put this in red so you guys remember that, in our course, we will always use 400R. We're not going to use 300 or 500. We always use 400R because that's what's available from the Canadian mills. Okay, 400R, which means 400 yield, and then R stands for regular. It means it's not weldable. Okay, guys, some of you think that every metal is weldable. Some rebar is not weldable. It means you cannot weld them with a welding sticks. Okay, but some they are. And so, you know, we typically, in most cases, 99%, we do not weld the rebar together. And remember this, we do not weld the rebar together. Okay? Yes, because assembly welding is super expensive. Welding is super expensive. I guess the welder hour is above $100. Okay? And a fresh engineer is only $30 something. Okay? Very, very expensive to weld the rebar. Now, on the same diagram here, we supposed to see another value, which another mechanical property is called the modulus of elasticity. Modulus of elasticity, we refer to E sub S. E sub S. So modulus of elasticity of steel, because shortly you will see E sub C, because we have two materials, So everything you will see sub S and sub C. Anytime you see sub S, it means steel. Anytime you see sub C, it means concrete. So guys, the modulus of elasticity is simply the stress over the strain. So the modulus of elasticity is the division of the stress divided by the strain. Remember, the strain is unitless, and that's why the modulus of elasticity units is the same as the units of the stress. Both of them, they are in MBA. And I think if you guys remember probably the first or second class, we said that here we're going to use 200,000 MBA as our modulus of elasticity. And this comes from the code. And you can see here is my clause from in the code. So it's clause 8.5.4.1, where it says the modulus of elasticity of the reinforcing rebar E sub S shall be taken as 200,000 MBA. Okay, now if the modulus of elasticity is 200,000 and the grade of the rebar is 400, you can simply find the strain at the yield point. One more time, if the modulus of elasticity is 200,000 MBA and the grade of the rebar is going to yield at 400, then obviously you can find the strain at the yield point. All you have to do is use this equation. So this number here is equal to 200,000, and this number here is equal to 400. And here we go. You can find the strain at the yield point, which is 0.002. Not very difficult. 400 divided by 200,000, you get 0.02. I need to remind you that this is a linear equation. I'm going to zoom in, and because this is not very clear, when you look at my diagram, you can see the diagram has a linear portion. So this part here, probably I have to draw it. So the part from here to there, this part here is a line equation. And then it goes horizontal. I'm going to zoom in more so you guys can see. So it goes horizontal, and that's happening during the yield. And then it goes to like necking and assembly snap off on the failure here. Okay. So guys, this is line equation. And line equation, you know from the math, From the math, you know that y is equal to mx. I'm going to box this out. So from the math, you know that y equal to mx. I know some of you don't like math. So y equal to mx. So on y here is the stress. Okay, so the y, the axis here is the stress. So the stress is equal to E sub S multiplied by epsilon S. Remember, the y is your stress, and the x is your epsilon or your strain, and the slope, the m is the slope of the line, which is the modulus of elasticity. What does it mean? It means if I go back to this diagram here, where can I see the E sub S, the modulus of elasticity? Simply, it is the slope of this line here. The slope of the line is the modulus of elasticity. So again, this is a quick revision. You've seen this, I guess, in strength of material. I think, I'm not sure who taught you this one, but I guess you had some experiment where you put a rebar in tension. Okay. Now, the next part is a very interesting part, types of reinforcing bars. So I'm going to zoom in. Okay. Guys, let me ask you for a couple of marks. Okay. You can see 3 different types of rebar. Which one is the most common one? Which one you will always see on site?
Top left, the regular.
Regular.
Okay, so I need to give you guys. I need to give you marks, So who said that? Jelly and Hamid?
No, it was Gord.
Yeah.
Gord? Okay, Gord. Thank you. So Gord, couple of marks here. And then was Jerry as well, I guess. Now, guys, true, yeah, true. When you look at, put your hands down, please. When you look at this picture here, there are three different types of rebar. One is very common, 99.99%. You will see this one here, which is called regular rebar. Sometimes, you know, because of the storage, it's kind of dark gray, but you will get the some kind of, you know, little bit of brownish because of the moist, huh? So this is very common. We use it to build all our structures, but sometimes, and I'll show you when do we use those. So you can see I put the names and you guys are responsible to identify which is which, huh? So this one is regular, this one is, look at the color, it's bright, it's fantastic.
Stainless steel?
Stainless steel, yeah, very nice, just like the cooking pots, huh? It's stainless steel and very expensive, very, very expensive. But look at the name, stainless steel, it means doesn't stain, huh? It's against corrosion. It's a different alloy. It is high resistance to corrosion. And myself, over my experience years, I did only one project. This project they use stainless steel. Okay, so this project was you know, the Heritage Bridge in South Calgary over the sea train, because those bridges they're supposed to stay for 200 years, and building them with just like a normal rebar is no good idea, because they get rain the entire year. They get some rain and there are lots of moist, and so they build with the stainless steel. Only one project because very, very expensive. Okay, but it looks beautiful, by the way, so you know. The last option, it's on the bottom right corner, which is called epoxy coated. So epoxy coated is the same thing. Corrosion is the enemy. We would like to protect our rebar, and sometimes some structure there is no choice. It has so much moist, no choice. Yes, in our building we try to make a building envelope. We're trying to protect our concrete inside, but some other structure we have no choice. It's already by nature or by the use of the structure is simply exposed to lots of moist, so lots of corrosion. So initially this option came like years ago and it was very popular, but I think now it's not very popular. Like epoxy coated is not really, to me, is not really good option, because simply what they did is they take a normal bars and simply they coat the bars with epoxy. They think epoxy is very strong and will provide protection, but guess what? I think it's even more worse than normal rebar. And I'll tell you why. Because simply as you move those epoxy bars from one place to another place, they scratch each other, and if you get a single scratch in the rebar, what happens? It works like a cathode, and simply your rebar will die very, very quickly, because all the corrosion will act on this spot here, not the entire rebar, but on a very small point. Okay, so anyway, not really very popular right now, not very popular. Okay. Now, I want to talk quickly about those other options. So sometimes we reinforce with the reinforcing bars, but we do have some other options. And again, probably in some other courses, you were quickly exposed to those. There's something called WWM or WWF, which is welded wire mesh or welded wire fabric. And very simple. Those are kind of they are prefab. They are welded together in a factory. They come to the site in either form of what you see. They come as flat sheet, or sometimes they come in a roll. It depends on the thickness of your rebar. For a bigger bar, you cannot roll them. So then what you do is you come as a flat sheet on the right. And if the rebar thickness is so tiny, then we can simply roll them, make them rolls. Now, why sometimes we prefer them? Because they are fast, very fast, very fast. No need to tie them because they are already welded and making a mesh in both direction, and simply save labor cost. Okay, so that's very good advantage. Where do we use them? We use them in slab-on grade, SOG, and we use them in concrete topping. So here, guys, I provide some picture. I'm not sure how clear you can see. This is a steel building, so it's completely steel. Columns are steel. The beams are steel. Even the flooring is steel, metal deck. So metal deck is very fast. However, it's not really usable. We cannot walk on those corrugated sheets. So what do? Is we come next and we place some very thin layer of concrete, very thin, probably 2.5 inches or 3 inches of concrete. We call them concrete topping on top of metal decking, okay? And guys, if you pour concrete by itself without any reinforcement, guess what? It's going to crack and will look ugly. So we place those rebar, and we, again, if we place rebar, it takes forever because simply we have to tie them, which will take forever. But if we place those WWM or WWF, so this construction will be very, very fast. Now, my last option for reinforcement, probably you hear also about this one. Maybe some of you already did some research on the first year about fiber reinforced concrete. There are so many. This is really, really a big topic. There are so many kind of material that can be used as reinforcement. Even some people, they use horse hair, human hair. They use it for the reinforcement. It's anything that you just mix it with concrete and simply increases the tensile stresses of your concrete. Okay, so you can see we have no rebar. You can see, look at the picture. So on the picture on the left here, we are pouring a slab on grade. So we have no rebar because simply those fibers will simply increase the tensile stresses and the performance in general. So we don't need any rebar because it simply stops the cracking. We only need rebar at very few points, which is, you can see here, there are even some rebar sticking. I'm going to zoom in. Okay, so you can see this guy here is a rebar. And simply this is happening only at very few places, which is, I wrote it here, under construction, at construction joint and expansion joint. Okay, so we place them very, very limited. And that's why it's very fast. You just jump into the warehouse. Okay, probably you can finish the entire warehouse in 4 days. I finished 6 years ago. I finished a warehouse which was 140 meter by a 40 meter in 4 days, from start to end. Very fast, but it's very expensive. Okay, and simply you do use it for high performance slab on grade. Okay, we still have a few minutes, so I'm going to talk about this one. This is going to be my last slide. This is going to be my last slide. So guys, when we design our members, we place not every a single size rebar. We place different sizes, and I will tell you when, because that's the design. So when we have more loads, we simply have more moment, and we have more moment, then obviously we need more rebar, and we add different sizes of rebar. Again, throughout the course, you'll understand, you know, and know more about bar sizes. But I provide here a table. This table comes from the manual, from the concrete manual. And this table, it shows you on the first column, watch the first column, please, to the left. So the first column, it says bar number, bar number. Start from the very top to 10M, tiny bar, small bar, and it goes 15M, 20M, all the way to 55M, okay? Now, I know you know these names, not you study so many classes in CVT, and 10M looks like it's a size, huh? It's kind of the diameter of your bar. On the second column, it says area in square millimeter. So if you take a cross section in that bar 10M, the area of the cross section is 100 square millimeter. Very, very important in my course. You need to know if I use 10M, the cross section of that 10M is 100. If I use 15M, it is 200. If I use 20M, it's 300, and so on and so forth. I bet you, when you finish my course, you will remember at least until 25M, because we will use them all the time in our design. Now, something also, some of you think, okay, you know, 10M is 10M, the diameter is 10 millimeter. That is not true. So what you see on the third column, the actual diameter of the member, okay, or the bar, 10M. That's how we call the bars on my drawing, but the actual diameter is not 10 millimeter, it is 11.3, and if you go through, you will see there is a little bit difference, okay? So the 25M, for example, is not exactly 25 millimeter, it's 25.2, okay, 25.2. In the same table here, there are some extra columns which they are not used in my class. I'm not going to touch the perimeter of the bar or even the linear weight of the bar. This is maybe used in estimating class, if you're doing an estimation for some structure, you need to order some rebar by weight. So it will tell you, or maybe you estimate the price. So simply use that last column to estimate the price, the weight, and then the price of the bars. Okay. Now, couple of things. One is, when you look at the picture on the right, this is kind of a sketch of how the rebar will look like. So you can see here is my rebar, and it says X, and then 20, and then sometimes nothing, and sometimes 400. So what are those numbers? Very important, huh? Very important. The 400, obviously by now you can guess, huh? 400 is the yield or the grade of the rebar. The 20 is simply the size of your rebar. From experience, you know, if you work in industry for maybe a year or two, I bet you don't have to even read the numbers. Just by looking at the rebar, but it needs, you know, a few times you go to the site, huh? You will kind of feel it's 10M or 20 or 25M, okay? But anyway, if you don't know, then here we go. Just look at the rebar and you will see the 20 is there. X is the mill, which we don't care. This is the name of the mill or the symbol for the mill that simply produced this bar. So very important, the 20, that's the size, because if you're doing an inspection on the design drawing, if it says 520M, you really have to make sure that there is a 520M. So the 5, you can count them, 1, 2, 3, 4, 5. How about the 20? We don't measure that, huh? You just look at the rebar and it's supposed to say 20. Now, you will see later on in my course, we will always use the diameter. For some reason, you will see next class, we will use the diameter for some calculations. So my question is, let's say I have 10M. Should I use 10 millimeter or 11.3 millimeter in my calculations?
11.3.
Jelly, it looks like what you're saying is true, and for sure, because that's the actual diameter. But the code is saying here something else. So the code here, read this statement, which I kind of a snapshot from the code. It says bar diameter for calculations. So the code is trying to give you some help, except for calculation involving bar areas. So if you're estimating the bar area, which is already there, you don't have to estimate it, then the bar diameter D sub B of metric reinforcing bar may, and look at this word, look at this, may, very important, may be taken as the bar designation. You know what? The word may will make Jelly correct, which means if you insist to use the actual diameter for 10M, which is 11.3, you're correct. And if you want to use from the code easement, so that's an easement, huh? Because trust me, when we do the calculation, it's way easier to use 10 because it's very rounded number. It's very easy. So the code is saying, give you kind of easement. You may, not you should, huh? If the code says you should, it means Jelly is wrong. If the code said may, it means yes, you may use the actual diameter, or you may use the bar designation at the diameter. But let me agree with you guys. Please write it down. Anytime in my course, I'm trying to make your life easier, because you will see if you need to, every time you need to find the diameter, you have to go to this table. However, if you use 15 millimeter as the diameter, then this will make your life easy. So let's agree. In my course, Tahir is saying, please use the bar designation for the bar diameter, which means in my calculations, if I need what is the diameter for the 15M, I know it is 16 millimeter, but again, use 15 because that's the code allowance. The code allows us to do that. Lastly, I'm going to end with this one. Some of you, yes, is going to work in Canada, and Canada here we use a metric system, and you will see 10M, 15M, 20M. But some of you may go to the States and work in the States. In the States, they don't really use metric; they use imperial, and they have a different way of calling rebar. Even in residential here in Calgary or in Canada, in residential. And sometimes get some shipment of rebar from the States. Sometimes you don't see 10M and 15M. Sometimes you see number 3, number 4, number 5. And what is number 3, number 4? Guess what? The number 3 is, it's an 1/8 of an inch. So it means when I say number 3, it means 3/8 of an inch. And 3/8 of an inch, if you do the math, because an inch is 25 millimeter, then it will be very similar to 10M. Number four is 4/8 of an inch, which is 12 point something millimeter, so about 13 millimeter. Okay. So anyway, without going into details, because I will never use this table in my class, but they have another table which gives you the imperial designation, like number 3, number 4, and so on. And then it also gives you the area and the area and the diameter in inches. And this table is used in the States, not in Canada. Okay. Any questions so far? Any questions so far?
Sir, I am just confused. What is that M stands for there? 10M, 25M.
Just a designation, same as designation. That's how we call the bars on our drawing. We call the bars 25M. It is not millimeter, it is just a designation or rebar name. Any other questions, guys? Any other questions? Okay. Any other questions?
What kind of plants do you have behind you?
Lots, my friend. Cactus, like, lots of cactus, like small ones. I have lots. I have lots of little palm trees. I love planting. Just give me a second. I'm going to show you something. Probably I should have stopped the recording because I don't want this to happen in my recording.
Yeah.
Okay, so stop recording first.